Okay, so now that we've seen what the limit of a function is, we can start thinking about differentiating and integrating. And so calculus is all about rates of change, how fast one variable is changing in respect to another. Some examples of rates of change: velocity is the rate of change of position with respect to time. Acceleration is the rate of change of velocity with respect to time. So let's consider an example. Let's think about dropping a basketball from a height of 1 meter from rest. So what I mean by that is at time equals 0 seconds, the velocity is 0 seconds as well. So it's starting with 0 velocity, and then it's going to fall to the ground. And I'm not going to go into how to calculate this, but at around 0.45 seconds later, the velocity is going to be 4.41 meters per second. Sorry, it's meters per second here. Okay, so this is 0.45 seconds is the instant just before the ball touches the ground, and that's the velocity at that point. So let's draw this on a graph, just so we can kind of visualize not x, time, and velocity. So we can kind of visualize how velocity is changing with time. So at t equals 0, its velocity is 0, so it's going to be right here. And at t equals 0.45 seconds, its velocity is 4.41. It's going to be somewhere there. And all of the acceleration in this system is due to gravity. So acceleration is due to gravity. So that implies that it's uniform. The acceleration is uniform. And if it's uniform, that means our graph is going to be a straight line. So we can just draw a straight line between these points. Okay, so let's try and find the acceleration. So what's the acceleration? That's our question. So acceleration is, as I said earlier, is the rate of change of velocity with respect to time. So that's like the change in velocity over the change in time, right? So the change in velocity, so the velocity started at 0 and it went up to 4.41. So the change is going to be 4.41. And the change in time started at 0 and it went to 0.45. So the change is 0.45. If you put it into your calculator, you can get 9.8 meters per second. Meters per second squared, sorry. And so what we've done here, let's think more closely. So what we've done is we've taken 0.45, so that's what this distance is, and then we've got 4.41, which is that distance, and we've said we've taken and so this is the rise, and this is the run, right? So it's going to be rise over run, and if that's familiar to any of you, that's the same as the gradient. So in a velocity time graph, the gradient is the acceleration. Okay, so I've just done this example just to kind of demonstrate that it's very easy to find the gradient of a graph if it's a straight line. What about if it's not a straight line? So let's consider the function f defined by f of x equals x squared. So let's draw the graph of this. F of x. It's going to look something like this. Whoa. That's better. Okay, so it looks something like that. Let's have a look. So the rate of change at a certain point, say this point, is just defined to be the gradient of the tangent at that point. So a tangent is just a line that just touches that point. And so let's just think of another point, say here, and let's think about the tangent at that point. So it's just going to be something like that. And it doesn't take a genius to say that these two lines are very different, right? Their slopes are very different. So the rate of change is not constant. So it's going to depend on x. It's going to depend on where it is in the on the graph. So but for now, let's just focus on trying to find one of these tangents. But I just wanted to observe that it's going to be different, and the gradient of f of x is going to depend on x. So let's just draw a kind of zoomed in version just on the positive quadrant. So it's going to look something like this, right? And let's take a point. I'm just going to call it x0. We can make so it's going to be quite hard to find out what this tangent is, but we can make an approximation, right? So at this point x0, we have, so it's going to cross this axis at f of x0, right? Now let's think, how are we going to make an approximation for, well, okay, well, we want this tangent, right? Okay, but it's not quite touching it, but you get the idea. We want the tangent that just touches at this point. So let's make an approximation for it. So let's just take another point, say, I don't know, up here, and let's just, so this is extremely zoomed in. So let's just say this is x0 plus h, and h is very small. So this distance here is really small. We're thinking about really small distances, right? But it applies to bigger ones, but for our purposes, we want them to be quite small because we want an accurate approximation. And so now what we can do is we can do the rise over run between these 2 points, and we can find the gradient of the line that crosses between them. So this is our approximation for the gradient of the tangent. So that green line is approximating that grey dotted line. So it's okay approximation, but we can do better. We can do better because we can make h a little bit smaller, and we can say let's do in this point instead, right? And this point's a little bit closer, and you can see that if let's get another color. Let's get another shade of green. So it's just gonna, so that this new approximation is gonna look something like that, and you can see that this line here is a lot closer to the grey dotted line than this one here. So as we're reducing h, as h is getting smaller and x0 plus h is getting closer to x0, our approximation is getting closer. So let's think about let's go back to here. Okay, so let's think about finding out what the gradient is of our approximation. What is that going to be? So this is going to be at f of x0 plus h. So we're going to do rise over run, right? So we want to find out what the rise is here. So that rise is going to be f of x0 plus h minus f of x0, right? And then the run, so here, so rise and then run, and so this difference is going to be x0 plus h minus x0. And we can see that these two are just going to cancel out to 0, and it's going to get f of x0 plus h minus f of x0 over h. Right? And I already said that as h gets smaller, the approximation gets more and more accurate to this line here, right? So we can take the limit, so this is where limits comes in, we can take the limit as h goes to 0 of f of x0 plus h minus f of x0 over h, right? And then that's going to give us what this line is, because as h approaches 0, as this x0 gets closer here, so we're picking points that are closer and closer and closer, and these tangents are getting closer and closer to our tangent that we want. Sorry, it's getting very messy now, but you kind of get the gist. So as h0 approaches, as h approaches 0, then our approximation approaches the true value of the gradient of the tangent, which is what we wanted. Right, so this leads us on nicely to our definition of a derivative. So let's get our formal definition out. So the definition is, okay, so the derivative of f of x. So this is like this is known as differentiation from first principles. So the derivative of f of x, written as f prime of x, is defined by f prime of x equaling the limit as h goes to 0 of f of x plus h minus f of x over h. And we've seen this before, right? We got to this on our own from here, right? But we did it at a certain point f of x 0, but it works for all the points on the graph, right? If this limit exists. So sometimes limits don't exist, but I won't go into that in this video. Okay, so that's what it means. That's what a derivative means. This is literally the definition of a derivative. So let's try and use this to find out what to formally prove what the derivative of x squared is. So differentiate from first principles f of x equals x squared. Differentiate, we should put respect to x. Okay, so yeah, let's start. So we've got f of x equals x squared, right? So f prime of x, so let's just make sure so we can kind of see our definition as well. So f prime of x is equal to the limit as h goes to 0 of f of x plus h, so that's going to be x plus h squared, minus f of x, which is just x squared, over h, right? So now let's just expand that bracket. So that's just going to be x squared plus 2xh plus h squared minus x squared, right? And these x squareds are going to cancel out, and that's over h. And then now you can see that these h's can cancel out as well. So now we're going to get the limit as h tends to 0 of 2x plus h. Now we can clearly see that as h tends to 0, this is going to go to 2x. So now we've kind of proven that the derivative of x squared is 2x. Now I just want to kind of like just show you this in terms of the epsilon delta definition that we went through in the last video. So let's just put this in a box and continue as if we didn't know it. So for any epsilon greater than 0, let's just let delta equal epsilon. So this is our relationship. So you can do some working out to kind of like get a good guess for what this relationship will be. And then, so let delta equals epsilon such that, so in our definition, it was h, so h is our x in our definition, minus a, but a is 0 because h is tending to 0, so it would be the same as writing h minus 0, but we don't have to, is less than delta. Then we have, so f of x is just, our f of x here is, so if you just think back to the definition, the equivalent of f of x is going to be the 2x plus h minus the limit, so we think the limit is 2x, right? That's equal to h, and we said that that was less than delta, but delta is equal to epsilon. So we've just proven that 2x plus h minus 2x is less than epsilon. And that's the same as sort of this function minus the limit, and then, yeah, so we're done. So in the next video, we're just going to go over integration and how limits apply to that.